Hello, everybody. My name is Jin Huang. I'm working on industrial automation system performance optimization over deeply embedded device. And here is Louis collaborating with me. So in this session, we are about to discuss the construction of secure microkernel for deeply embedded devices, also known as IoT. You know, IoT is just nothing, just buzzword. You know, we introduced a new open source implementation named after F9 microkernel. It is efficient for low power devices with security design in mind. So, an American expert said security is not a product, but a process. Do you remember OpenSSL? Habits 3 years ago. It's a nightmare. And let's check out various known firmware attacks related to IoT security. So the first one is in 2013, a researcher at Georgia presents Mac-10s which inject malware into iOS devices by modified USB charger. And another case in the next year, the researcher at the SR Lab modified firmware of USB devices which do something evil, including first to emulate a keyboard and issue command on behalf of the login user. Second, it spooned a network card and changed the computer's DNS configuration to redirect the traffic. So you might say, how come I'm not so stupid? But according to another research, recent research, user will pick up and plug in USB flash drive after they find usually. After the USB drive is connected, the evil firmware will be activated. This is the reason why we should always use, you should take the secure consideration in mind. Last year, ARM announced the availability of ARMv8m, which provides trust zone extension. It can enable bus level protection in hardware. ARMv8m core can fill the requested DMA access initiated by unprivileged code on bus level, while for ARMv7m, it requires more software API. MPU, which stands for Memory Protection Unit, MPU banking in ARMv7m reduced the design of a secure operating system. And the secure OS partition on a private MPU with full control, and the OS keeps the privilege mode for fast IRQ. So why do we need another kernel? The reason is the consideration of trusted computing base. If TCB gets smaller and smaller, we can focus on the detailed verification on security and further attack. So as seen from the slide, bigger and bigger kernel always suffer from weakness and uncertainty. Linux is the best example to illustrate the critical risk from software quality. The microkernel approach, as you already know, tries to eliminate the problem arising from big kernels by strictly following the principle of least principle, which implies nothing allowed by default. A capability is is a communicable and forgettable token of authority. It refers to a value that it refers to a value that references an object along with an associated set of access rings. A user program on capability-based operating system must use capability to access an object. In other words, microkernel should be minimal with hardware-enforced separation. It is interesting that the design competition between interface first and implementation first is interleaving. So you can see, first is a Matrix. Matrix itself is interface first, and then Unix, microkernel, and Linux, and maybe the last one might be SE4, which is interface first. But the competition is still going. The mechanism inside microkernel are the only trusted components, including address space, IPC, and thread management. All other services are done at the user space. There are 3 generations of microkernel development. The second generation is L4, and the third one is SE4. You can forget the first one, which of the poor performance. So let's start from the second generation. The second generation of microkernel is known for L4, and L4. I mean, the implementation of L4 is a family. Is known for be fast because of smaller cache footprint, which implies much faster IPC. L4 itself is not exactly an implementation, but a family of implementation. SE4 is the most advanced one, licensed under GNU GPL. L4 is widely commercialized by Qualcomm and Open Kernel Lab. The typical use case of L4 is to offer isolation from software in other cells so that existing software components can be reused in new design. Furthermore, the compatibility of the dispatching multiple operating system workload across multiple physical CPU might be reduced by means of microkernel-based hypervisor. The migration from the generation to the third generation microkernel is to resolve the following problem of improper memory abstraction, which resulting in the possibility of denial of service attack. SE4 is a notable implementation of the third generation microkernel. And F9 is the new microkernel designed for IoT, or deeply embedded devices. The design consideration of IoT are, first, to support dynamic nature of IoT devices. Second is to prevent the acceleration of data while traversing the network. The third is the advanced power management. Another requirement is over-the-air update firmware mechanism. The switch to a new version is only operated when the newly downloaded content is fully validated. So what does F9 provide? F9 itself is free distributed in BSD license in two closure license, which allow commercial use, and is optimized for on Cortex-M cores by means of fast IPC and well-structured design. Security is an important consideration as well. In addition, F9 provides a flexible development mechanism inspired by Linux kprops in order to provide directed optimization, PDO or PGO. F9 microkernel attempts to eliminate the risk of existing unavailable system by small TCP on the file patches and solid system isolation. The next generation of device F9 microkernel is named after BSEC, implemented as a third generation microkernel. The architecture looks like the diagram, where F9 microkernel acts as a hypervisor to isolate the two domains. One is the untrusted domain, where all applications runs. The normal application runs in untrusted domain. And another is the trusted domain, where everything is fully validated. F9 follows the fundamental principle of F9 of L4 microkernel. That is to implement address space thread management IPC only in the previous kernel. And everything is almost built from scratch to facilitate the features on Cortex-M series, including NBIC, which stands for the nested interrupt support, bit banding, and MPU memory protection unit. Memory management is split into three concepts. First, memory pool represents manages the area of the physical address space with specific attribute. Second, flexible page describes an always align region of address space. Unlike other L4 implementations, flexible page in F9 represent MPU region instead. And the third is address space, which made out of these flexible pages. Okay. Interrupt handling in F9 can be handled in both kernel thread or user level thread. To improve power efficiency, F9 introduced tickless kernel, which results better kernel consumption than the common approach driven by system ticker. The idea of a tickless kernel is that CPU only wakes up by event instead of periodical timer. So let's compare. Think of the context switch overhead. Single context. Okay. This is the diagram illustrates the overhead in context switch. And tickless scheduling can avoid timekeeping overhead. How can it do? So tickless kernel, in F9 implementation, it enter tickless right before going to CPU idle state, and set interval of next timer interrupt as the delta of next event. So you can see if your timer is periodic, your interrupt handler wake up periodically, it consumes more energy But if your kernel is only driven by external event, so such as network, such as the touchscreen event, it can get more reduction in energy. Okay, so I would like to introduce the K-probe implementation in F9. K-probe is a dynamic instrumentation inspired by Linux kernel, allow a developer to gather additional information about kernel operation without recompiling or rebooting the kernel. K-probe in F9 can be used for OTA update or remote debugging purpose. At the moment, F9 provides partial party support and some system profiler, so you can monitor the system resource and figure out the location you want to optimize. F9 microkernel is commercialized by Genesis company, which is based in USA. Genesis, the company, use F9 to provide smart solution for IoT called Redis K1. The communication between device and the server is based on WebSocket subprotocol, and the data exchange is encrypted. So you can see the device is based on the Cortex-M, which is very efficient in both power and the security design. BStack is the next generation of F9 microkernel. We learned from Microvisor, which is a sub-project of an embedded operating system, and we implement F9 microkernel in BStack as a lightweight alternative. BStack can facilitate the memory protection of Cortex-M, including advanced features in NV8M I mentioned before. It is heavily inspired by SEL4, moving other mechanisms with security enhancement. The security enhancement and the facility show outside the kernel. Its target is the low-power IoT devices, and it's very lightweight. You can see it only 2,000 line of code. BStack use capability or key to manage resource with the add or object or reference and a state of ring. Okay. BStack itself only provides 3 system core, which consists of sender, receive, and yield. The same as almost the same as SEL4 does. Sorry. So I'm going to represent the memory protection mechanism.
Okay, hi, I'm Louis, and I'm going to take the MPU 101 here. And because F9 and BStack is intended to be on ARM v7m, and in ARM v7m there isn't any MMU at there, so you didn't have page flow protocol to use. But there is a protocol of MPU is memory protect unit, and we can use this unit to provide a basic memory manage for Cortex-M application or kernel. So on Cortex-M4 there is 8 region you can set it on it, and on M7 you have 16 region you can set on it. And every MPU region you can set some feature on it, like the TEX capability or the access permission for the user or not user for the privilege or for unprivileged. And the most important thing is you can set this execution never bit. And the execution never bit is to represent one thing is if you enable this bit, this region will not take as executable memory. So you can prevent some attack like the buffer overflow attack on it. Okay, so there's on Cortex-M there is the memory region is flat. So on, for example, Cortex-M4, they will have 4 GB of the memory, like the diagram. And so now, if we consider there is a BitSec is running now, and the PC register is at this address. If an attacker put the malicious code at the 2000/400 address, and it uses anyway to set the PC go to this address, then the CPU will try to fetch the next instruction at this address, right? So if this is done, then the attack is bingo. But today, if we set in the MPU region and set it to the not execute, like the yellow part of the memory. So MPU region, we can set the base to this address, and we can see this place, for example, is a peripheral for maybe serial or other things. So we can set the size is the power of 2 to 12. There's a restriction of this is that we can only take the power of 2 size for the memory protect size. And so in this case, the range is from 200/400 to 200/500. And if the attacker tries to fetch the instruction in 200/408 as the next instruction, in this time, MPU will catch this invalid memory access and trigger MPU to generate a memory managed fault exception. So this time, attacker won't execute this code, but captured by the memory managed fault handler, and then we prevent the attack on this situation. And we can use the open OCD and GDB to simulate this problem. So we use OpenOCD and enable GDB by target stand to the port, and monitor set symhost to enable reset and load it again. And we can predefine some memory address to the MPU. Then we can set the attribute to MPU register, and using OpenOCD provides the instruction and MWW, the memory write word to this register address, and we can redefine the PC by using MWW to simulate the problem I mentioned before. So we can then see the result on the GDB that it will cut by the memory managed fault exception handler. Okay.
I'm not familiar with Mac, so I need some time. So what's okay. This is here is the case study for the RTOS integration. Here RTOS stands for the implementation like FreeRTOS or other implementation, for example, on embedded operating system. So in the case study, we will show how BStack hypervisor works. The integration is not RTOS API emulation layer of a simulator. Instead, it runs actual RTOS code derived from the on port, including the schedule. And RTOS system layer implement some mechanism. For example, the first thing is the allocation and the deletion of operating system object, like task, queue, and heap. And also, it has to provide mutex with priority inheritance to ensure the operation timeout and the time slicing with preemption. And as far as you can see from the diagram, there are two contexts in RTOS and the BStack integration. The first thing you have to consider is task context. Another is interrupt context. So think about the scenario that the interrupt context, how the interrupt context works. First, BStack has to model thread execution code used to run RTOS, and also it has to be tweaked to run the the interrupt handler code, such as ISR, and finally it provides some virtual interrupts. So the virtual interrupts itself is the message model in the form of the supervised code, and there is a system gate introduced in NV8. So NV8M. So if your hardware is based on NV8M, BStack itself can directly use SG to be the base of the hypervisor. If your hardware is not NV8M, for example NV7M, such as on Cortex N3 or N4, BStack provides the emulation code for the system gates, and the RTOS first sends BStack IP message through SG in order to request a context switch and to enable or disable the interrupts. So let's check the diagram again. So you think the existing RTOS, like FreeRTOS, is already implemented, and BStack act as the hypervisor. It provides some virtual interrupt facility to perform the virtual interrupts as well. And the message dispatch loop multiplies the interrupt context. So let's to make some conclusion. Minimized TCP is feasible for building secure IoT operating system, and L4-based design bring the software isolation mechanism. It is known to work and already used in some commercial products. Cortex M4 processor enable real-time availability and memory protection facility to develop hypermodal low-cost platform. And F9 microkernel already takes this advantage to build an efficient hypervisor and RTOS infrastructure already. So we would like to ask the developer to put some attention on F9 microkernel development and we share some use case, successful story, and sample requests to us to improve the F9 microkernel. So, do you have any question? Okay.
Yes, I have one question, and please don't take me wrong. I really don't mean it in a bad way. But if you claim that you have been inspired by the L4 kernels and by the SCL4 in particular, what are the benefits of starting a new code base and not taking SCL4 as your starting point and tweaking it in a way you want?
Okay, that is good question. The question is why not just tweak SEL4 for the IoT OS? SEL4 itself consists of more than 9,000 lines of code. But for the devices like Cortex N3 and 4, you have limit RAM and flash storage. So it is almost impossible to use SEL4 directly. But we can take the advantage from SEL4, such as capability system. So you can deploy the fine grain protection for given resources with timing consideration which is quite important for IoT devices.
But most of the SCL4 code is generated actually from the executable specification. So is there a possibility to somehow change what is being generated, so what components or maybe what parts of the kernel are being generated to make the code smaller? I'm really just asking.
Yeah, the question is interesting because as you say, most of the code are generated by SEL4 preprocessor and some formal models, but it's quite difficult for us to maintain. So we try to put F9 to RISC-V. It takes about 2 weeks, but for SEL4 I cannot imagine the feasibility. Do you have an? Okay.
Do you have anything running on V8M already?
Sorry?
ARM V8M trust zone.
Oh yeah, just I could not say because it's I haven't signed some NDA, so I cannot sorry, so I cannot say the exact model. But I already work on the simulation environment for the on face model based system. So the working prototype is already works. So you can I can show you off time. Yeah. So if you use on V8M, it has a mechanism like system gate, which is quite efficient. You can eliminate the extra. I mean, you can eliminate additional section without frequent context. I mean the exception return overhead. Yeah. So if you lack of the system gate, you have to implement the switch by just normal exception handler. And have more question? Okay. Okay. Nice to. It's my pleasure to present F9 microkernel and the incoming BSEC. There are some interesting references, so you can check the first one. It is essential material discussing about the migration from L3, L4, and SEL4 in 20 years. And the the second one is the lecture. I think the tutorial is quite interesting and informative. And if you are interested in the ticketless kernel, you can check the last one. We have another presentation. You can find it on SlideShare discussing about the ticketless kernel, K-timer, and how Cortex-M works. Okay, thanks for coming. Thank you.